Okay, let's start with exercise 1. You have two sets A and B in the domain of a function f. Okay, and B is a subset of A. Then prove that f of B is a subset of f of A. Okay, so for a general subset C of the domain, we call that f of C is given by all the numbers such that there exists some vector x and c such that f of x is equal to y. Okay, so it's all the values that f can take ranging over all the vectors in C. Okay, so we need to show that if B is a subset of A, then f of B is a subset of f of A. Okay, so let's take any number, let's say y in f of B, then you have to show that y is also in f of A. So if y is in f of B, well, then we know, following this definition, you know that there's some vector x in B such that y is equal to f of x. Okay, so this is simply by definition of f of B. Okay, so if x is in B and B is a subset of A, well then it follows that x is in A. Okay, so x is in A and y is equal to f of x, well then it follows immediately that y is in f of A, so every element of f of B is also an element of f of A, and we're done. Okay, so the second question, let A and B be two sets in the range of f. Okay, so now we're not talking about sets in the domain, but in the range. So, and B is a subset of A again. Then prove that f minus 1 of B is a subset of f minus 1 of A. So first, let's define the set f minus 1 of B. Okay, we haven't seen this before, but so if we have the domain and the range of f, then if we go via f, then it's f of, let's say that this is a set, f of c is everything that maps every value, possible value that is taken up by f of x for some value x and c. So if you have the same mapping, and here b is the range, then everything that maps to b is in f minus 1 of b. Okay, so f minus 1 of b is a set of all the vectors x in the domain such that f of x is in b. Okay, so that's basically what this notation means. Okay, so we have b as a subset of a, and we are asked to show that f minus 1 of b is a subset of f minus 1 of a. Okay, so we take a vector in f minus 1 of b, and we have to show that it's a subset of f minus 1 of a. Okay, so if we take x in f minus 1 of b, well then following the definition of this, then we have that x of f of x is an element of b, and then b is a subset of a, so from this it follows that fx is in a, and if fx is in a, well then x is in f minus 1 of a, so indeed f minus 1 of b is a subset of f minus 1 of a. Okay, question number 3, we have a mapping f from some domain to some range, and you have a collection of sets ai, okay, in the range of f, and you have to show that f minus 1 of union I of ai is equal to the union of I of f minus 1 ai. Okay, so in particular we have to show that every element in this set is also in this set, and every element in this set is also in this set. Okay, so let's take an element in f minus 1 union of ai. Okay, then x is in the set of all vectors, let's call these y and d, such that y is in union I AI. Okay, and this is in fact an if and only if. So y is in the set. Well, if and only if f of x is in union I AI. Okay, and of course x is in D. Okay, if f of x is in union of I AI, well, this is the same as saying that there exists an I such that f of x is in AI, and then of course x is in D. Okay, well then in this case there exists an I such that if you take this together, then this is nothing else than x is being in the element of f minus I AI, and the fact that x is in f minus 1 of A1 or f minus 1 of A2 and so on and so on. This is nothing else than saying that in the union over all I, sorry, I should have that x is in the union over all I of f minus 1 of AI. Okay, and these are all equivalences, so this is the same thing as saying this. So you have indeed the equivalence of these two. As the second part, we're asked to show that f minus 1 of the intersection of over all I of AI is equal to the intersection over all I of f minus 1 of AI. Okay, so again, let's take x in f minus 1 over the intersection of I of AI. This is the same as saying that x is in the set of all the vectors, let's call them y, in the domain, such that f of y is in the intersection over all I of AI. Okay, this is the same as saying that x is in the domain and f of x is in the intersection of I all AI. This is the same as saying that x is in the domain and for all I f of x is in AI. Okay, if it's in the intersection, then it has to be in all of them. If it's in all of them, then it's also in the intersection. Okay, and then we can bring the for all I in front. So for all I, this means that x is in the set of vectors y and d. Okay, so it's a vector in D, and f of I is in AI. This means that for all I, x is in f minus 1 of AI. And if it's in all of these sets, x is in every one of these sets, so it's also in the intersection. So x is in the intersection of I of f minus 1 of AI. Okay, so this shows that these two things are equivalent. Okay, question number 4. So what do we have? We have S and T, they are non-empty subsets of R, and we have two functions f. So if you have T, then you have S, and then you have R. So f goes from T to S. Okay, so it's a function like this. And G goes from S to R. So G has domain S and image R. Show that f is continuous at x. If f is continuous at x and G is continuous at f of x, right? So x maps to f of x, and then G maps f of x to some number here. Then G after f is continuous at x. Okay, so I haven't defined this function yet. So what's this function? G after f. Well, if you evaluate this function at a number x, this is G of f of x. Okay, so basically it's the composition of these two functions here. That's G after f. Okay, so the function G after f goes from here, from the domain T, and it maps an element from the domain T to the real numbers. Okay, so now the question is that if f and G are continuous, then this function is also continuous. Okay, so what do we need to show? We need to show that if we have a sequence nt that converges to some vector x and t, well, if this is the case, then g after f, this function of xn, converges to g after f of x. Okay. So xn goes to x. Well, we know that f is continuous, right? So this means that f of xn converges to f of x. Okay, so f of xn, call this, right, so basically we don't need to take vectors because they're subsets of R. Okay, so these are basically numbers. So call this yn. Okay, so and call this y, right? Then this says that yn converges to y. And this is a sequence in the set S. Okay, so because g is continuous, we know that g of yn converges to g of y. Okay, so this is continuity of f, and this is continuity of g. However, yn is nothing more than f, so we have g of f of yn converges to g of f of, should be xn, sorry, g of f of x. Okay, this is simply by substitution, and g of f is g after f of xn, and g of f of x is g after f of x. Okay, so in the end we have that if xn converges to x, then g after f of xn converges to g after f of x. Okay, question number 5. Show that the definition of continuity as we used it in the lecture notes is equivalent to the epsilon delta definition. Okay, so the epsilon delta definition is the following. You have that for all epsilon bigger than 0, there exists a delta bigger than 0, such that for all y in the domain, if the distance between x and y is smaller than delta, then the distance between fx and fy is smaller than epsilon. Okay, and we need to show that this entire thing is the same or is equivalent to our definition, which says that for all sequences xn d, the domain, if xn converges to x, well then f of xn converges to f of x. Okay, so we need to show that these two definitions are equivalent. So let's try to prove this. So this is an if and only if condition, so you have to show that the top demonstrates the bottom and that the bottom demonstrates the top. Okay. So before we start, let's have a look here. This says that xn converges to x, and we know by definition that this is the same as saying that for all delta bigger than 0, there exists a number in delta and n, such that for all n greater or equal to this n delta, distance between xn and x is quite smaller than delta. Okay, so this is the same as here. Also this here, fxn converges to fx. Well, this is the same as saying that for all epsilon bigger than 0, there exists an n epsilon and n such that for all n greater or equal to this n epsilon. And now we need to take the distance between fxn minus fx is smaller than epsilon. Okay, this is just rewriting the definition of convergence of a sequence to the convergence of this and the convergence of this. Okay, so let's now show first that the top implies the bottom. Okay, and we're going to use a proof by contradiction. So we're going to assume that this holds, right? So assume that for all epsilon bigger than 0, there exists a delta bigger than 0, such that for all y in the domain, fx minus y smaller than delta, and fx minus fy is smaller than epsilon. Okay, and we're going to assume that this here is violated. Okay, so we have to negate this. Okay, so we assume that there exists a sequence. Okay, so there exists a sequence xn and d such that this is false. Okay, so this is an implication, p implies q. If we negate this, then we have p and not q. Okay, so what's p? P means that for all delta bigger than 0, there exists an n delta and n, such that for all n greater or equal to this n delta, xn minus x is smaller than delta, and not q, so we have to negate this here. So, and there exists an epsilon bigger than 0, such that for all n epsilon and n, there exists an n greater or equal to n epsilon, such that fxn minus f of x should not be the absolute value, should be the absolute value, right? Fxn minus fx is greater or equal to epsilon. Okay, so basically let's enumerate this. Here we have 1, and then we have that there exists a sequence xn such that this holds, 2 holds, and here 3 holds, and we would like to find a contradiction. Okay, so from the third point here, we have that there exists an epsilon such that for any number far enough into the sequence, f of xn minus f of x is greater or equal to okay, and here we have that for all epsilon, something else happens. All right, so we can take this epsilon here and plug it into this definition here. Okay, so then we know that if you use this epsilon here, well then we know that there exists a delta bigger than 0, such that for all y in d, if x minus y is smaller than d, then fx minus fy, okay, so these should all be vectors here, is smaller than epsilon. Okay, so this is for this particular epsilon here. Okay, so what do we say? We say take the epsilon that we have found in 3 and use in 1, and then we know that there exists a delta that satisfies this. Okay, so now we have found the delta here, and then we know that 2 holds for every delta. Okay, so we can use this delta and plug it in into this here. So take this delta, okay, that we have here and use in 2. So what do we find if we do this? Well, we found that there exists in delta and n, such that for all n greater or equal to this n delta, xn minus x is smaller than delta. Okay, so for all n greater than n delta, xn minus x is smaller than delta, and we know that if this is true, right, if we use here xn instead of y, then x minus xn is smaller than delta, so it should follow from this that for all n greater or equal to n delta, while xn minus x is smaller than delta, so it satisfies this condition. So we know that fx, again this should be the absolute value, minus f xn is smaller than epsilon. Okay, so there exists an n delta, just as for any n greater or equal to this n delta, fx minus fxn is smaller than epsilon. However, on the other hand, we know that for all n epsilon here, there exists something greater that fxn minus fx is bigger than epsilon. Okay, so if we set this in here to be equal to this n delta here, then you have our contradiction, right? So this says that for anything that is beyond, this difference has to be smaller than epsilon, and this says that there always exists something beyond this number such that this distance is greater or equal to this epsilon. So these two things give a contradiction. Okay. Okay, so far we have seen that this definition implies this definition, and now we're going to establish that this definition implies this definition. And again, we're going to use proof by contradiction. So we're going to assume that this is true, right? So for all sequences, if the sequence xn converges to x, then f of xn converges to f of x. Okay, so sorry. And we're going to assume that this is false, right? So p implies q, so we assume that p is true and q is false. Okay, so assume that for all sequences xn and delta, xn converges to x, implies that f of xn converges to f of x. Okay, so, and we assume that this is false. Okay, here, sorry, we have to assume that this is false. So we're going to negate this here. So we're going to assume that there exists an epsilon bigger than 0, such that for all delta bigger than 0, there exists a y in the domain, such that x minus y is smaller than delta. Alright, so we have to negate this implication, p implies q. So if you negate this, then you have p and not q, so, and fx minus fy is greater or equal to epsilon. Okay, so this is a good exercise in terms of negating formulas. Okay, so we know that there exists an epsilon such that for all delta, there exists a y in the domain, such that the distance between x and y is smaller than delta, but the difference between the function values is greater or equal to epsilon. So knowing this, we're going to, there exists an epsilon, right? So take this epsilon bigger than 0. So we know that for all delta bigger than 0, there exists a y in the domain, such that x minus y is smaller than delta, and fx minus fy is greater or equal to epsilon for this particular epsilon here. So this holds for all delta. Okay, so what are we going to do? We're going to take a sequence. We're going to take a sequence of deltas smaller and smaller and smaller. This will generate a sequence of y's, right, whose distance from x gets smaller and smaller and smaller. So in the end, we're going to get a sequence xn, yn, basically, that converges to x, right? The distance goes to 0. And because fx minus fy is greater or equal to epsilon, the function values will not be able to converge to each other, right? Because the distance from f of x will always be epsilon far away. Fyn will also be always be epsilon far away from f of x. However, this condition here requires that the two have to converge to each other, so this will give us the contradiction. Okay, so let's do this. Let's put, for example, delta equal to 1. Well, then I know there's a y1 in the domain, such that x minus y1 is smaller than 1, which is a delta, and fx minus fy1 is greater or equal to epsilon. Okay, we can take a delta to be equal to 1/2. There exists a y2 in the domain, which is that x minus y2 is smaller than 1/2, and fx minus fy2 is greater or equal to epsilon. Okay, we can continue doing this. After round n, you have delta equal to 1 over n. There exists a yn in the domain, all vectors. Forgot to put all the vectors. So x minus yn is smaller than 1 over n, and fx minus fyn is greater or equal to epsilon. Okay, and you can continue doing this indefinitely long. Okay, so in general we get the sequence yn in the domain such that x minus yn is smaller than 1 over n. Okay, for all n, so this converges to 0. So by the convergence lemma we have that yn converges to x. Okay, so we have a sequence in the domain that converges to x. So by the first assumption here, we need to have that, if you call this 1, so by 1 we have that f of yn converges to f of x. On the other hand, f of y1 is epsilon far away from f of x. F of y2 is also epsilon far away from f of x. F of yn is epsilon far away from f of x. So for all n, f of yn minus f of x are at least in distance epsilon from each other. And then on the other hand, we know that the two converge to each other. So this is the desired contradiction. Right? It's impossible to converge to a value if you stay in distance epsilon from this value. Okay, so I think this was the last exercise of this part.